Well, let me introduce Ondřej Kaman, my collaborator from the Institute of Physics. He will speak mainly about magnetic nanoparticles, so it's yours.
Yeah. Thank you. So, dear ladies and gentlemen, this talk or presentation is supposed to be structured in 3 parts. So it will be about fundamentals, about mostly physical characterizations, and also about synthesis of magnetic cores. It would be very logical to start from the last point, synthesis, then go through the fundamentals, through some physical principles and phenomena associated with magnetism on nanoscale, and then end up with characterizations. However, I think from the didactic reasons, I would like to re-alter this structure. So we will start with some physical characterizations to get some basic insight into properties of magnetic particles. Then we will speak about fundamentals. And finally, after lunch, in the last part, we will mention briefly some basic methods of synthesis and peculiarities of the given materials. So let's go to the first part. The idea of this part is to present a basic set of physical or even chemical characterizations that are really recommended for magnetic nanoparticles to be, for example, employed in MPI studies or in some medical applications. I would like to show you what you should do from the material point of view to present your material well and to work with well-defined samples, with well-defined properties. I don't want to go into some principles, details. I don't want to repeat some texts from textbooks, or I don't want to give these university lectures. You can easily find that in the textbooks or on Wikipedia. But I would like to provide you rather a practical guide with some hints, with some maybe highlighting of problems, and I will mainly speak about information that you can get through these methods. So let's go. Let us imagine a situation that you prepared some magnetic nanoparticles in your lab, and you would like to do some fancy biological or medical studies with these particles, and you are considering what characterizations are necessary. So, depending on the purpose of the study and also depending on the materials, I would suggest mostly these characterizations. So, maybe just at the beginning you will start with powder X-ray diffraction. This is the main method, just to analyze your sample in terms of the phase composition. For example, you will intend to prepare some ferrite particles, but you would like to check if you prepared the ferrite and it is not contaminated by some other components like hematite. So you will run powder X-ray diffraction. Very likely you will be interested in the size of your particles, in their morphology, so you would like to do some microscopy, and definitely I would recommend the transmission electron microscopy. In certain cases, if you are not just focused on simple iron oxides, if you are preparing nanoparticles of some complex oxides, if more than one metal is involved, you should do some accurate chemical analysis of the product. If it is not guaranteed that during the synthesis all the metals involved are really quantitatively incorporated into the product. So in that case you need this chemical analysis, and that will be the X-ray fluorescence analysis, XRF. Of course, dealing with magnetic particles and with their behavior in some magnetic particle imaging studies, you should do also some basic magnetic characterization. if you are working, for example, with iron oxides, and especially with iron oxides containing ferrous ions, I mean, if your samples are not just based on iron 3+, if you suppose that iron 2+ is involved, like in magnetite nanoparticles, you should prove that. You should do the Bessbauer spectroscopy. I will explain that later. And of course, if some experiments on suspensions are involved in your studies, which is a typical case of imaging, you should do some proper study of colloidal stability. You should analyze hydrodynamic size, maybe zeta potential. So you will need to do some light scattering studies, and you will probably start with dynamic light scattering. And finally, and maybe most importantly, if you are measuring, if you are studying some quantities that are dependent on concentration, for example, if you want to compare MPI signal of different samples, you should do some proper chemical analysis to be sure that you know the concentration of the particles in the suspension. So, and we will go systematically through these methods, and I will try to explain what information you need, and also I will show some problems, but I don't want to, as I mentioned, I don't want to repeat the principles. But maybe the first method to be described is this powder X-ray diffraction. Maybe you already know from the high school the Bragg's law, which can be simply derived, but maybe just this picture, which shows the simple procedure how to derive this Bragg law, is not very accurate. I mean, it's even wrong, but it is like it works. It's a model based on a reflection of X-rays on some planes in the crystal, but the process involved is not reflection, but it is diffraction. And like in summary, it can be analogous in certain point, which allows to derive these conditions for the Bragg diffraction lines, but like the physical basis is completely different. So I don't want to go into these details, but I feel that it's important to say this. So if you have your powder sample from the lab, and if you want to do powder X-ray diffraction, most probably some powder diffractometer with the Bragg-Brentano parafocusing geometry will be available to you. It's schematically shown here, and like the important point in this geometry is the localization of the X-ray tube and the detector, that both of them have the same angle with respect to the plane of the sample. So here is the detector, here is the X-ray source, the X-ray tube, here is the detector, and here is your sample. So in this case, the sample is introduced to some dish like this. Well, it's the sample holder is basically just a shallow hole where you adjust the sample. Where you adjust the sample with the surface of this holder to have a defined position in the vertical direction. This is important. So do not put a large pile of your sample there, or do not put just few grains at the bottom. It has to be really aligned. If you have a small amount of sample, you can consider using some non-diffracting sample holder, some non-diffracting plate, for example, a cut of a silicon single crystal cut made in that direction that it will not diffract, and you will put the tiny amount of your sample onto the surface, and then you will exactly position the plate maybe in some soft matter, on top of some soft matter in some holder, and you will place it to the Bragg-Brentano geometry with the tube here and the detector here, sample here. So what information is provided by powder XRD? As I mentioned, this is the principal method to analyze the phase composition. So you can determine the crystalline phases present in the sample, but just the crystalline phases. You won't see amorphous components because they don't provide this kind of diffraction. They don't have any Bragg diffractions. Of course, you can analyze the diffractogram to determine some crystal structure parameters. So, but typically this is used when you already know the crystal structure, or you suppose certain crystal structure, and you are just determining certain parameters of the crystal structure. So basically, you are refining the crystal structure. Importantly, you can also analyze the size of crystallites, because there are some effects that affect the width of diffraction lines and that are related to size of particles. Also, you can analyze some strain effects, maybe some compressive strain or some general strain related, for example, to some chemical heterogeneity in your solid solution. And you will see also effects of preferred orientations. We will see some typical XRD patterns. So on your left side, you will see four patterns measured on some nanomaterials. Well, this first pattern, it's XRD for a perovskite phase composed of lanthanum, strontium, manganese oxide. And you clearly see some diffraction lines that are very characteristic for the given structure type, for the perovskite. And basically all phases with this type of structure will have exactly this pattern in XRD, and depending on their lattice parameters, depending on the composition, just the lines will be somehow shifted, or the intensity will be somehow modified. Which is very well seen in the third pattern in this green, or as well as here. In these samples, there are actually two perovskite phases. One is the lanthanum strontium manganite, and the other one is barium titanate, which also has perovskite structure, but it has different lattice parameters. It has different composition, but actually it has very similar structure. So you can see that there are like two perovskite patterns in this pattern, and they are shifted because of this Bragg law. The lattice parameter is different, and that's why the Bragg diffraction occurs at different angle. Like, it's also interesting to see the blue pattern, which is this material coated with amorphous titanium dioxide, and as you can see, there is absolutely no signature in this pattern of of another phase. You see just the pattern from the first case, and there is nothing more. So you can see that the amorphous admixtures are typically not manifested if the content of the amorphous phase is not huge. If the content is large, you can see some additional very broad peak, which has no sense for some analysis. But it can also be like this, that you will you will not see any signature of some amorphous component in the sample. On the right side, you can see two types of nanoparticles of zinc ferrite, roughly 5 nanometer sized particles and roughly 15 nanometer sized particles prepared by thermal decomposition. They are, this is the story for the afternoon, but so we have just two samples with the different size of particles and their XRD patterns. And this is the pattern for the smaller particles, this is for the larger particles. They have like the same arrangement of diffraction lines, but for the sample with smaller particles, the peaks are much broader because of this line broadening given by the size of particles. This is a more detailed view of patterns of the manifestation of some amorphous components. So here you can see such four samples of magnetic particles coated with amorphous silica, from a thin layer of around 5 nanometers to a thick layer with a mean thickness of around 21 nanometer. And as you know, this is well-known material, the silica. So the silica is amorphous, and therefore there are no Bragg diffraction lines in powder XRD patterns. However, for large amounts of this amorphous component, you will see such broad band which is arising at lower angles. And this is some scattering related to amorphous silica, but it is not actually that much correlated with the content. Okay, you can see some correlation that it is increasing with the content of the amorphous component, but no really clear physical model can be suggested for quantification. You cannot do any serious analysis. At one conference, I saw an attempt to quantify the amorphous component based on adding some additional component in the Rietveld analysis, but it's completely insane. There is no physical justification for that. If you like to quantify the amorphous component, you may consider something like mixing your sample with some additional well-crystalline phase. I don't know, mix a known ratio of your sample with a known amount of, or mix to create a mixture of your sample and the crystalline phase in a known ratio by weighting it carefully, grinding it in an agate mortar, and then if you measure XRD, you can quantify the crystalline phase in your original sample with respect to the amount of the edit phase, and based on this ratio and based on the ratio of your in your mixture, you can calculate the content of amorphous phase, but you cannot calculate it directly from the pattern. So this is another nice example. So this is a XRD pattern of some spinoferrite of manganese zinc ferrite, which is measured on really high quality. We have a very high signal to noise ratio, and in such high quality XRD pattern, you might discover some tiny admixtures that you will not see in standard patterns. So you know, sometimes I would say that researchers sometimes publish low quality patterns, or they don't care about recording really nice data, and often some tiny admixtures are disappearing in the noise. However, today with the availability of excellent detectors and with the availability and rather low costs of excellent diffractometers, you can really record very nice data, and you can maybe discover, or you can reveal some admixtures in your samples. In this case, it was less than 1% of hematite in the ferrite sample, and I would say that this is not a shame. This is not a shame that the sample is not pure. If someone had measured this sample on a low quality, then it would have been a pure sample. But if you measure it on high quality, you will reveal something like this. So please be careful when doing powder XRD and try to collect nice data. Then another issue which you can encounter during XRD analysis, maybe some samples won't be stable in air because of maybe some moisture in air. They will become hydrated. They will because they are hygroscopic, or they will react with carbon dioxide, forming some carbonates. Or maybe you intend to work with, for example, metal iron nanoparticles, which will basically burn in air. So there can be different issues causing the air sensitivity. Also, some samples might become decomposed under the irradiation by X-ray, or some samples will lose their water. So I would recommend to do the measurement as a series of rather fast, short scans that you can later sum. So typically we are measuring 5 to 15 scans, or rather fast scans, and then if we don't see any change, we can sum them. Of course, if you are working with some inorganic well-stable materials where the stability is known, you needn't to do it, but in certain cases when you have some varies, for example, when you measure some salts of transition metals, not hydrates but anhydrous salts, such samples might be very hygroscopic. So, for example, in this case, we observed that something is happening there, that even some additional phase is arising during the measurement. So you can reveal such processes in the series of scans, or and if you reveal that, you can consider some procedure to secure your sample against the air. You can use some special sample holders with airtight cavity. You can mount your sample under some Kapton foil or mylar foil. So let's go to important issues. I mentioned that there is the phenomenon of line broadening, which is mostly related to the size of crystallites. However, there are 3 contributions in the line broadening. Generally and inevitably, there is all the time some contribution from your diffractometer. So there is also some instrumental broadening which you should determine. All the time you should determine the instrumental broadening by measuring some well-crystalline, strength-free standard, I don't know, for example, lanthanum boride 6 is often used, or some nice metal like wolfram can be used, tungsten. Then there is the second contribution to the line broadening, and that is the contribution of given by scattering on domains of limited size. If the coherent diffraction occurs only on some nanoscale domains, there is this broadening, and we can analyze this broadening. And often the parameter that is calculated in this analysis, this parameter should be understood as some volume weighted mean size of coherently diffracting domains is usually denoted as the mean size of crystallites. By all means, you should not interpret this as some true size of individual particles. But it's a very representative value that is measured on a larger amount of sample, and there is no space for user bias, and it is volume weighted. It is somehow accurately defined, so it's nice. And also there are strain effects, like as I mentioned, if you have some solid solution and the composition inside the solid solution varies in your sample, like it slightly varies between individual nanoparticles, like the lattice parameters of individual nanoparticles will be different, and it will cause some minor shifts of the Prague diffractions in the pattern. So that's why there is this broadening related to the chemical strain or to the chemical heterogeneity. And there are many important issues, but I think we should move forward. I would mostly point out one issue. This line broadening is very useful for this analysis of size of crystallites, but on the other hand, the line broadening can obscure your XRD pattern in terms of the symmetry of the crystal structure. For example, in this figure, you can see 3 or 4 diffraction patterns of some perovskite phases. Again, it's quite complex perovskite, this lanthanum strontium doped with terbium. And there are different samples prepared like by 2 different methods, nanoparticles prepared by 2 different methods. There is also a nice bulk sample with large grains, with well crystalline, and in this inset there is even a 4th sample of slightly different composition. And like looking at seeing these regions, these tiny regions of this most intense diffraction line, you can see that the situation is quite complex. In 2 samples, in the nanoparticles prepared by molten salt synthesis and in salt gel nanoparticles, of these compositions, you can see like a broad diffraction peak. Actually, there are 2 very close diffraction lines here, 104, 111, but they are very, very close to each other. So you cannot distinguish them, not even in the bulk sample. But the problem is that the line broadening is really large, and you can see just a broad peak. In contrast, for the bulk sample, you can see some fine structure, or if you see the measured pattern, you can clearly observe some asymmetry, some additional components. And this component somehow indicates the symmetry, the specific symmetry of the given crystal lattice. In this case, it is orthorhombic. So you can see it easily in well-crystalline sample. However, if you prepare some nanoparticles of small size, and if you consider the line broadening, this fine structure, these asymmetries might be completely obscured. So for nanoparticles, it might be difficult to analyze some distortions, some deviations from some simple symmetry. However, in this case, these 2 samples are rhombohedral or trigonal. and in contrast, this bulk sample, as well as this composition with lower strontium content, are orthorhombic. And you can prove it also for the nanoparticles, but you have to analyze the data carefully, running the so-called Rietveld analysis, like fitting of the whole pattern and considering the statistics. So let's go further. Preferred orientation. I would say this is a trivial effect if you have some needles or some platelets in your samples. If the crystals are of this form, then maybe during the sample preparation they will assemble in some preferred orientation, and this will affect your XRD pattern, because you would like to measure XRD pattern with random orientations with all random orientations. But if there is some preference for assembling the flat crystals in certain manner, it will be distorted. But you can involve this effect in the analysis, but it can somehow complicate the thing. Yeah. I think now it's time to introduce some basic crystal structure which you are usually working with, and that is namely the spinel crystal structure. You know the mineral spinel, which is like the prototype of the whole group of compounds or crystal structures that are based on a closed packed arrangement of oxide anions in space that are like hard spheres put in layers one on top of another one. And there are actually two ways how to arrange these hard spheres. But in this case, the oxide anions are arranged in a sequence of three layers, ABC, which are not precisely aligned, like they are not, they are slightly shifted. So there is this sequence ABC, and if you describe it geometrically, and if you see it from the viewpoint of crystallography, you will see that it forms such face-centered cubic cells. So this is the arrangement of oxide anions, and you can clearly see in this crystals in such arrangement that there are some holes between the oxide anions, and there are two kinds of holes: the tetrahedral holes and octahedral holes or sides. So, and these sides are occupied by the cations. And there are two types of cations, let's say A and B, and the A represents cations that enter to the tetrahedral sides, and B describes cations that enter the octahedral sides. So we have one tetrahedral cation, two octahedral cations, and four anions. So in the normal spinel structure, this tetrahedral cation is divalent cation like manganese 2+, and the cation entering octahedral sides is the trivalent cation like aluminium 3+. But it can also happen that the divalent cation goes into the octahedral sides and replaces half of the trivalent cations, which then goes to the tetrahedral sides. And there are many important compounds that belong to this structural type, especially various spinel ferrites, manganese zinc ferrites, cobalt zinc ferrites. The well-known magnetite is actually the inverse spinel with this kind of situation that the divalent cation is going to the octahedral sides. But also, for example, thiospinel, graphite. And importantly, the well-known maghemite is also derived from this crystal structure, And you can describe meghemite as like iron 2 plus deficient magnetite. It has actually the same crystal structure, but there is less iron on octahedral sites. So you can formally describe it as some spinel with vacancies on octahedral sites. And from the viewpoint of structure, these vacancies might be completely randomly positioned. It can be completely random, or they might be positioned in some regular pattern with certain symmetry, specifically with tetragonal symmetry. And of course, there can be a varying degree of ordering. So you can prepare a meghemite with completely randomly distributed vacancies on octahedral sites, or fully ordered meghemite with vacancies in some clear pattern. Usually 3 different structural models are employed to describe the situation. 2 of them are cubic and 1 is tetragonal. And this will slightly modify the XRD pattern. However, considering the situation of nanomaterials, some nanoparticles with broadened diffraction lines and with lower intensities, you will unfortunately not see many differences typically. And the main problem is that in typical samples you cannot distinguish these different forms of meghemite, and you cannot distinguish them from magnetite. Actually, you cannot distinguish the magnetite from the completely disordered meghemite in terms of random order of vacancies. They will have typically the same XRD pattern. And this is a very sad situation that somehow researchers in the field of magnetic nanoparticles do not reflect this simple fact. And you will see thousands and tens of thousands of research articles where someone measures XRD pattern, compares that with PDF database, and will claim, okay, this is magnetite. But typically, it won't be magnetite. Typically, it will be some non-stoichiometric phase between magnetite and meghemite, partially oxidized to meghemite. But some people tend to conclude based on XRD patterns, not seeing some special features of the fully ordered meghemite, that it is not meghemite, that it is magnetite. So unfortunately, the literature is really flooded with wrong interpretation of XRD patterns. So let's go further. This is an example from a laboratory of my colleague Michal Babič, who is preparing some meghemite nanoparticles by coprecipitation method, and he is using some oxidizing agent that will transform the magnetite into meghemite. So you can be pretty sure that it is not magnetite, it's meghemite, and you can see the XRD pattern compared with some typical diffraction lines of magnetite structure that are the red vertical bars, and compared also with the diffraction lines of fully ordered meghemite with the tetragonal symmetry, and there should be these additional diffraction lines, but they are very weak compared to the most intense diffraction line, and they needed to be developed in relation to the partial ordering of vacancies. And in this case, you cannot see any signature of such ordering. Actually, this sample is meghemite with fully disordered vacancies, whose XRD pattern is very, very similar to magnetite, there are some minor differences in intensities, but they will disappear in these patterns of nanoparticles. So just remember that you can't use XRD to distinguish magnetite and mechamite. So let's go to electron microscopy. I cannot go into the principles. I will not repeat some stories, but I will just mention that there are many modes of transmission electron microscopy. There are also some special techniques that are suitable. So besides the bright field imaging, besides some conventional imaging by transmission electron microscopy, you can, for example, measure scanning transmission electron microscopy. You can install some EDX detector to your microscope, and you can do, for example, chemical mapping. Often it is combined also with electron diffraction, so you can do the imaging of the material, and you can measure electron diffraction using electron beam instead of X-ray. Also, there are such useful methods like electron energy loss spectroscopy, which can be also used for chemical analysis, but it can distinguish also different oxidation states. So you can do chemical mapping accompanied by mapping of oxidation states. And there are some issues related to such studies. First, you should really do representative imaging. You should really collect representative TEM images for your samples at different scales. However, you should consider some problems. You should consider that some samples might be sensitive and they might undergo degradation under the electron beam of pretty high energy. So you may consider decreasing the aperture. You may consider some measures like this. Also, if you intend to do EDX analysis and chemical mapping, you should maybe think about the choice of the grids, of the right grids for your sample, not to interfere with the EDX analysis. Maybe if you are analyzing copper ferrite, you wouldn't like to use the most common copper grids, but maybe you would like to employ nickel grids. So just some examples from our laboratory. All the time we are trying to do really representative sampling, representative imaging at different scales. So for example, in this case, it was a sample of epsilon iron oxide doped with aluminium, and it was coated with some silica. And this is just a print screen from our folder with TM images, where you can see up to 30 images at different scales, with low magnification, where you can see a large number of particles, so you have really some representative idea about the sample, down to large magnification, where you can see some details. So try to do it like this. Try to get at least some images in low magnification, seeing a large amount of particles, and then these detailed images. Maybe you will go for some image analysis. You would like to describe your sample, the sizes in some quantitative manner. So the data are definitely useful for that, and what to analyze, what to report. All the time I suggest to calculate the arithmetic mean. Do not, like in the first stage, do not make any assumption about the distribution. And also in your papers, it's really better to include this just the arithmetic means, just some descriptive statistics of your sample before going to some assumptions regarding the size distribution. So you can measure some particles in your images. There are many programs to do it. and you can collect a large number of values. Then you will calculate some arithmetic mean for the size. It's trivial for spherical particles or for cubes. In case of some random shapes, you may consider measuring the area, quantifying the area, and calculating some equivalent diameter of 2D projection of a hypothetical spherical particle with the same area of the 2D projection. And then you can calculate this equivalent diameter, calculate the arithmetic mean. Of course, you should somehow show the distribution. So you will probably calculate the standard deviation or the corrected sample standard deviation. But you have to distinguish this from the standard error or standard deviation of the arithmetic mean. This is very important. This is somehow related to the confidence interval around the arithmetic mean, whereas this quantity, this parameter describes the distribution. So just another recommendation: when reporting values like this, you should really state what you are reporting. So I really recommend to use either clear nomenclature like this and this, or to include at least in supplementary some definitions like this, because the literature is again flooded with some standard deviations, some reported standard errors, but there are different approaches, and if you do not declare, or if you just mention some deviation or put some number in parentheses, it has absolutely no value if the reader doesn't know what you are speaking about. Nevertheless, you may like to do some assumption about the shape of the distribution. So typically, the growth of nanoparticles is leading to the log normal distribution, but this is like the most simple situation. It is not valid universally, but it's very common. So you may apply some assumption like this. Again, there are different formulations of the log normal distribution. You can see like different expressions here. There might be a natural logarithm of some sigma, and there is also some confusion arising around this. So I would like to make this clear. If you formulate your log normal distribution like this with this type of sigma, then this sigma parameter is the standard deviation of the natural logarithm of the size. It is not the standard deviation of the size. Alternatively, if you introduce logarithm into this formula of some sigma, it won't be again standard deviation of the size, but it will be so-called geometric standard deviation, and it is not trivially related to the standard deviation of the size. So do not use units for such sigmas, and you have to understand that this sigma is really the deviation of logarithm. And this parameter d0 is not the mean value, but it is the median value. If you want to calculate the diameter, you can use this the mean diameter. You can use this expression. Also, if you are interested in the standard deviation of the mean diameter, it means standard error of the diameter, then you have to recalculate the median by using this formula, etc. So again, when reporting some values evaluated based on assumptions of about size distribution, I recommend to introduce, to declare the formulas at least in a supplementary. Then it's clear. Because there is a huge confusion in literature about these standard deviations. So let's go to another technique available in transmission electron microscopy, and that's the high resolution imaging, or now it's quite common that people have access to high resolution transmission electron microscopy. So it's very useful to go to large magnification and to see your particles in more detail. For example, these micrographs are from the normal mode of transmission electron microscope, like from lower magnification, and if you enter the high resolution mode, you can see some very nice details like these patterns. They are called lattice fringes, and they are directly related to crystallinity because they arise as the result of constructive interference of the transmitted light and diffracted light. So this is it's manifestation of electron diffraction, and it proves the crystallinity of your particles. Of course, you can also measure electron diffraction. Like we saw the X-ray diffraction, so this is very analogous experiment. In this case, you can see a large area covered with particles or with their agglomerates, and the measurement of electron diffraction over the whole area. So you will collect such circles, and when you integrate the circles, you can convert it to the pattern which is analogous to the powder X-ray diffraction, and you can see again the clear pattern of the spinel structure, and in this case it was the manganese zinc ferrite, so it makes sense. And this will again show the crystallinity of your sample, and you can also consider measuring electron diffraction on a single particle if you have some nice microscope. So then you can do analysis for a single particle. Chemical mapping. I mentioned that you can include include energy dispersive X-ray fluorescence analysis in your microscopy. It's very well available nowadays, and you can analyze chemical composition on whole maps of the sample, and you can prove, for example, that it is really chemical homogeneous, that some dopant is distributed in the whole sample. This technique is also very useful when studying some core shell particles composed of different compounds or different phases. In this case, it was a composite formed from this perovskite and barium titanate, another perovskite, and we can see some lanthanum strontium manganite cores coated with barium titanate. And this kind of imaging was very important because both the phases have similar contrast in the bright field imaging, and you cannot clearly distinguish them. So just by chemical mapping, you can see that we have this core shell structure. You can do also some quantitative analysis, studying, for example, studying the standard error of the composition, or how the composition varies in individual particles or in some regions of the sample. So, but it's important to know that the EDX analysis, quantitative analysis like this, is not that reliable in terms of the composition, in terms of the true composition, because it's quite complex and there might be some spectral interferences, and there is contribution of absorption within the sample, so you need to run some matrix corrections, and you have to do careful analysis, and it's also dependent on the geometry, on many parameters. So at the end, you needed to collect very, very accurate composition, but you will collect some calculated composition that should be quite stable within your sample. So it can provide really information on variation, but you should not trust the composition in terms of the real chemical composition of the sample. And for that case, you need another analysis if like as I mentioned, if you prepare sample containing 2 or more metals, and if you apply some procedure where it is not guaranteed that all metals are incorporated, then you should analyze the chemical composition of the product. And you should analyze it on the macroscopic way, on the macroscopic level, namely by X-ray fluorescence analysis, which is analogous to EDX in TEM, but this is a separate analysis on a macroscopic sample, which is optimized for accuracy, and it can be calibrated well. So you can get some reasonable accuracy, and it's really important analysis, and I will demonstrate it on this case. This table shows 3 samples of zinc ferrite, cobalt ferrite, and cobalt zinc ferrite prepared by thermal decomposition, where the initial starting materials were mixed in this ratio. Like we mixed some zinc acetylacetonate and iron acetylacetonate in the stoichiometric ratio of 1:2, and we did the synthesis. Here it was cobalt acetylacetonate and iron acetylacetonate 1:2, etc. However, during this synthesis, during the thermal decomposition, some components may remain in the reaction mixture in the solution, and some components will, and only some components will enter the sample. So the composition of the product might deviate strongly from the initial composition of the reaction mixture. And you can see it based on the XRF analysis, for example, in this case, that we obtained only a much lower amount of zinc in the final product compared to iron. So it is really, really important. And I believe it's time for a small coffee break, or we have 90 minutes in total. Mm-hmm. So, and I'm afraid I'm already speaking more than 45 minutes.
So I suppose you can continue. We have another half an hour.
Okay, so we have.
If you want.
No, I will be happy to continue, and we have in total like 30 minutes ahead. Mm-hmm. Okay, let's go. And so. Just my main message is don't forget the proper accurate chemical analysis done on the macroscopic level. Well, Base-Bauer spectroscopy. This is kind of a special technique which is unfortunately not that common as it should be in the papers on magnetic nanoparticles, because like majority of researchers is working with are working with iron oxides, and they are working with this magnetite or mechamite or some mixtures between that, and they should analyze the samples correctly in terms of the real oxidation state of iron and real composition. And the Base-Bauer spectroscopy, or 57 iron Base-Bauer spectroscopy, is the only way how to do it, I would say. So if you decide to prepare meghemite, fully oxidized iron 3+ oxide, then you needn't to do Base-Bauer spectroscopy if you are really sure that it is only iron 3+. However, if you are dealing with magnetite or with any system containing iron 2+, or especially when working with metal iron particles or with some iron nitride particles, you have to do this just to determine the actual oxidation state of iron. I think that we don't have enough time to go into the details, but just I will mention that this technique is usually measured in the transmission geometry, and the spectra, the collected spectra look like this. So and it is the dependence of the intensity on the velocity of some source of the gamma rays that is like vibrating, or that is moving forward and backward, just to do the energy modulation by the Doppler effect to modulate the gamma beam to cover different energies of the transitions. And the resulting spectrum contain quite rich information, because basically all crystallographically non-equivalent sites with it's actually even more complex, but in the first approximation, let us conclude that all crystallographically non-equivalent sites of iron will be manifested by a separate component in the spectrum, by a separate subspectrum. So, for example, in this case, epsilon iron oxide, this structure has four iron sublattices, four crystallographically different sites. So we have four components in the spectrum related to these different iron positions. And moreover, the sample is based on nanoparticles, and the core is quite well crystallized and magnetically well ordered, but the shell on the surface is typically slightly disordered, and slightly the magnetic ordering is suppressed there. So there are other effects which make it different. So we should separate also the surface volume into separate components. So actually, in this case we did analysis with 8 components separating the core and shell. So and if you manage the analysis, the fitting, you can collect information regarding the individual iron sites. And importantly, the spectrum contains information about the oxidation state, and also about the neighborhood of these iron atoms. So you can use it to, for example, to determine the quantity of iron in the tetrahedral and octahedral sides of the spinel structure we mentioned earlier. And you can determine at the same time the amount of iron 2+ and iron 3+. I think I should skip certain details, but just briefly, the analysis of Miss-Bauer spectra provides the set of hyperfine interactions, the set of hyperfine parameters. And there are 3 hyperfine parameters: isomer shift, quadrupole splitting, magnetic hyperfine field, and all these parameters provide some useful information. So, but the main message regarding Miss-Bauer spectroscopy is that it really enables to quantify different forms of iron, different oxidation states. It enables to distinguish them in different sublattices and quantify them. And you can collect also some information on, for example, on spin state of the iron, if it is low spin, high spin, and so on. And just now a practical example. I mentioned that by using XRD you cannot distinguish megamite and magnetite. However, if you measure Miss-Bauer spectroscopy, and if you are able to quantify iron 2 plus and iron 3 plus, you will be absolutely sure about your sample. If it is really pure stoichiometric magnetite, or if it is partially oxidized to mechamite. Typically, it will be some non-stoichiometric mixture between magnetite and mechamite. It's quite difficult to get a nice, well-defined nanocrystalline magnetite. And but it is even more powerful. Like in this case, we prepared some zinc-doped iron oxide nanoparticles by thermal decomposition. Actually, there were two samples. And in literature, it is often assumed that the samples from the thermal decomposition are based on magnetite, that it is really stoichiometric magnetite. But usually researchers do not prove it. But in this case, it was more complicated because of the presence of zinc. And so at the beginning, we had some material which can be generally described by such formula. So there are the tetrahedrosides, then there are the octahedrosides, and we have to assume that there is all the time some iron 3 plus and maybe some iron 2 plus, and there is the zinc, and the zinc 2 plus can be either in tetrahedrosides or in octahedrosides. And moreover, we cannot be sure that it is stoichiometric magnetite. Maybe some iron is missing because it's getting oxidized to iron 3 plus. So we have to introduce an unknown number of vacancies on octahedrosides. So, and if you formulate such a general description, you have there 3 variables, x, y, and delta. So we need 3 equations to resolve this situation. And as I mentioned, you will measure XRF to determine exactly the ratio of zinc and iron. So this is your first equation. And you can measure Miss-Bauer spectra, and you can quantify the amount of iron in tetrahedrosides, the amount of iron in octahedrosides. You can express it as a ratio and assemble this equation based on the formula. And similarly, you can quantify the amount of iron 3 plus and amount of there is some mistake. It might be fine, because this is the total iron in tetrahedrosides, this is the total iron in octahedrosides, and this is the total, this is the iron 3 plus in tetrahedrosides, and this is the iron 3 plus in octahedrosides. There can be also a different approach. You can quantify the ratio of iron 2 plus and iron 3 plus, or iron 2 plus there and here. So, but this is also independent. We have a third equation. One equation is given by XRF, and 2 equations are given by this analysis. So 3 equations for 3 parameters, and we can resolve the situation. And we can get such formulas that will describe the material in detail. And interestingly, this sample, the zinc ferrite prepared by the thermal decomposition, was indeed purely stoichiometric zinc-doped magnetite with no vacancies in octahedrosides. The other sample, somehow treated there after the preparation, was already partially oxidized to some mechamite. So this is just to show the power of Miss-Bauer spectroscopy, and also again I will repeat, you cannot claim anything about the identity of your iron oxides. You cannot claim anything about the oxygen stoichiometry, if it is iron 304, iron 203, or some mixture in between without such analysis. Another powerful tool is neutron diffraction. But again, we don't have time to go to details, but this can help to resolve even more complex situations. For example, we mentioned the manganese zinc ferrite, which contains 3 different metals. And maybe if you are interested in the real structure, in the real cation distribution between the tetrahedrocytes and octahedrocytes in this spinel structure, you should consider measuring neutron diffraction, because even if you measure XRD, if you measure Meßbauer spectroscopy, you cannot resolve the situation. There is another metal, and you cannot distinguish certain metals in XRD because they have very similar scattering factors. So you have to employ another diffraction technique, like neutrons, where the scattering factors of individual atoms might be quite different, and it will help to distinguish them. So by combining Meßbauer spectroscopy and neutron diffraction, we can completely describe the structure of such a system. We can exactly determine the amounts of individual cations on the tetrahedral and octahedral sublattices. And moreover, as neutrons interact with magnetic moments on the different atoms, we can also obtain some information about the magnetic ordering. We can resolve the magnetic ordering, and we can quantify the magnetic moments of individual sublattices. But let's go further. Let's go finally to some physics on nanoscale. This was just devoted to characterizations. Now we will speak about some physical issues. So, but now you already know something about the material. So we will start with such an idea of ferromagnetic material. If you have some proper piece of ferromagnetic or ferrimagnetic material, it has a multi-domain structure. It means that the grains are composed of uniformly magnetized domains that are separated by domain walls. However, if you start to decrease the size of such grains, sooner or later you will get to a certain limit where this structure is not energetically preferred anymore. Specifically, this structure with the multi-domain composition decreases the magnetostatic energy. This is just optimization of magnetostatic energy. But also the domain walls have some energy cost. And if you decrease the size of the grain, the gain in the magnetostatic energy is not large enough to cover the energy costs of the domain walls. So, and at that moment you will enter the single domain state. So it means that the particle will be uniformly magnetized, and it will still behave as a ferromagnet or as a ferrimagnet. It will still show some remanence, some coercivity. It will be blocked. It will show a normal hysteresis loop. However, if the particle is small enough, or if the temperature is large enough, it may easily happen that the thermal energy, will overcome the energy barrier between the reversal of magnetic moment of the particle between two orientations of the z-axis, and the thermal energy will cause the magnetic moment to rotate basically freely, or to relax, to reverse between the two orientations. So, and this phenomenon is typically called the Nel relaxation, and it is leading to super paramagnetism. So at temperature high enough, or for particles small enough, we are entering the super paramagnetic regime. I wouldn't say that there are superparamagnetic particles. There are no superparamagnetic particles. There are ferro or ferrimagnetic, magnetically ordered particles that can be either in the Bloch state or in the superparamagnetic state or regimes. But this description is of course dependent on your view, on the time scale of your view. If you will observe the particle long enough, maybe you will see after a long time some relaxation. You will see this transition to the opposite direction of the easy axis. So you will see some reversal. So the concept of superparamagnetism or of this state is also dependent on the time scale of your observation. So it is relative. Superparamagnetism is nothing absolute. It is dependent on your time window. And there are different techniques. So some material may appear as superparamagnetic or within one technique, and it may appear blocked in another technique. In typical situations, you are studying magnetic particles with some split magnetometry, and the time scale of such procedure is of the order of 10 to 2 seconds. If you apply Meßbauer spectroscopy, the time scale is much shorter. The time scale of Meßbauer spectroscopy, where this relaxation is also manifested, is around 10 to minus 7 seconds. If you apply ferromagnetic resonance, the time scale is maybe 10 to minus 10 seconds. So then you will conclude different findings. So we can, by doing some simple considerations, we can formulate the limit for the single domain particles. And we can also describe the process of the Nel relaxation of this reversal of magnetization. And the crucial parameter in this description is the Nel relaxation time, which is dependent, of course, on the energy barrier and on the thermal energy. There is some pre-exponential factor. This is like some attempt time. This is a time between two attempts, jump attempts to overcome this energy barrier. And the energy barrier is, in the very first simple approximation of uniaxial anisotropy, is a volume-dependent barrier, dependent on the volume of the particle and on some constant, on some effective anisotropy. Now, if you consider, and there are other considerations, like this is valid only for non-interacting particles, which is typically not true. But the situation is more interesting in suspensions. You are working with aqueous suspensions of some colloidally stabilized particles, and they can also rotate in the suspensions. So you have to consider potential rotational movements. And the magnetic moment may relax, may change also during this rotational, due to these rotational movements, and it is described by another relaxation time, by the Brownian relaxation time, which is dependent on the viscosity, also on, of course, on the hydrodynamic size of particles, and on the thermal energy. And if both processes are involved, you have to combine them, and you can combine also these relaxation times into an effective relaxation time like this. So this was the introduction. And now, how is it with the magnetization of the sample? Let's see the magnetic response of typical ferromagnet in DC magnetic field. If you measure the sample on your magnetometer, and if you analyze the hysteresis loop, you will see something like this. Typical loop of ferromagnet with multi-domain structure. If you prepare nanoparticles of the same material with a size small enough, you will not see the loop, but you will measure some unhysteretic, typically some unhysteretic response like this. And you may think that it is super paramagnetic. It needn't to be super paramagnetic. It can be also still blocked, but just the coercivity might be very, very low. So you should consider also a situation that it might be still a really blocked sample, but very magnetically soft. But let us speak about the nanoparticles in the superparamagnetic state now. Let us speak about this region of the relaxing particles. And let us see the magnetization of the ensemble of such particles in DC magnetic field. The magnetization will be described by the Langevin function. You have surely heard about this function. There is a parameter given by the spontaneous or saturation magnetization, by the volume of the particle, there is magnetic field, and again thermal energy. So this is the typical Langevin function, and of course there is some rescaling to the spontaneous magnetization and rescaling to the content of magnetic particles in the system. So this is the simple description of the magnetization of ensemble of magnetic particles in DC magnetic field under certain conditions, under certain simplifications, that there are no interactions and that the particles are isotropic, so magnetic anisotropy is disregarded, and so on. Nevertheless, in typical samples you have some size distribution, as we saw in TM. So and you have maybe made some assumption regarding the size distribution, like with the log normal distribution. So you may need to do integration of the Langevin function over the given size distribution. So you may describe the magnetization of the sample by such simple equation, and the crucial parameters come from the transmission electron microscopy. But this is the simple case of the DC magnetic field. But in magnetic particle imaging, you are interested in the response of magnetic particles to alternating magnetic fields. So if we apply alternating magnetic field, we can do the rigorous analysis, but it's quite complicated because the dynamic magnetization is for a suspension of magnetic particles. It is affected by the Snell relaxation, by the Brownian relaxation, and unfortunately the working frequency of your AC field, like in MPI, the working frequency is quite high, and the relaxation is quite slow. So it means that the magnetization response is not given by some equilibrium magnetization. It is not equilibrium state, because the relaxation is slow and the magnetic field is changing very quickly. So we are in some non-equilibrium state, and it's getting tricky. So, like in the first approximation, we can use the Debye theory, which was originally derived for electric dipoles, and it is based on such a simple differential equation which describes the time derivative of magnetization. This is the instantaneous magnetization of your suspension in magnetic field, in alternating magnetic field. And there is some dependence of this derivative, quite logical dependence, on the difference between the instantaneous magnetization and the equilibrium magnetization to which the system would come if there was enough time available. And then there is there is some scaling parameter which is the inverse value of the effective relaxation time. So this makes sense, but unfortunately this simple description completely disregards the Larmor torque. So this description is based on just on the potential energy, and it disregards the torque. So you cannot, for example, you cannot derive the precession. Nevertheless, it is very useful and very didactic, and if you consider, for example, that you have alternating magnetic field in this sinusoidal form, so it is harmonic alternating magnetic field, and if you just focus on fields with lower amplitudes, you can solve this equation and arrive to this expression, which describes the complex AC susceptibility, and it is a very well-known expression in the magnetic community for the complex AC susceptibility. The magnetic response of the sample is still of the sinusoidal form. Actually, it is shifted by p-half, and there is this in-phase component, out-of-phase component, and the amplitude of this response is omega dependent. It depends on the frequency and also on the relaxation time. However, the situation is more tricky for larger amplitudes. Nevertheless, there you can assume that this equilibrium magnetization can be written like through the Langevin function, because the equilibrium magnetization of the superparamagnetic system is described by the Langevin functions. So you can describe the equilibrium magnetization by the Langevin function, and you can transform this description to a Fourier sum of the basic term and higher harmonics term. And you can solve, with this description, you can solve this differential equation, and you can arrive to a solution for the dynamic magnetization, for the dynamic instantaneous magnetization, which will be again a Fourier sum of the basic term and higher harmonics term. And each of these higher harmonics will be described by this expression. So we have a clear physical description of the dynamic magnetization based on this theory, and this is quite straightforward, and you can use it, for example, to consider your magnetic particle spectroscopy data. But it is not the full description, and I think we don't have enough time for the full description. But I will just briefly mention that the rigorous full description of the magnetization dynamics in the suspension in alternating magnetic fields is based on the Fokker-Planck differential equation, whereby some probability density can be calculated, describing the probability of finding the particle orientation and the magnetic moment orientation in certain angular region. And this is the right way how to, for example, how to simulate the dynamic magnetization of your particles during MPS or MPI experiments. And I wonder what amount of time we have. This is just the end. So, so I think So the main conclusion is that there is some unique physical behavior of magnetic particles on the nanoscale. There are some new phenomena like this Snell relaxation, and there are also some special effects in magnetic properties, and you may observe finite size effects, surface effects, and some special physical phenomena which are not directly related to MPI or MPS. But for MPS and MPI, it's important to understand that it is based on the dynamic magnetization in alternating magnetic field, and the simple, straightforward view is provided by the Debye theory, but the Debye theory cannot describe rigorously the dynamic magnetization, and you have to apply this approach, for which you need to run some simulations, and there are also many parameters involved. You need to determine magnetic anisotropy. Of course, we have there the relaxation times. We have there the relaxation times, both the Snell relaxation and Brownian relaxation. We have there spontaneous magnetization. But using suitable numerical methods, it can be solved. Yeah. So yeah, this is the end. So any questions? Yeah. But you were the first one.
Ondra, please, when you have been describing the Mossbauer spectroscopy, so I have met a special problem that if I prepare some nanoparticles, so and put it for the Mossbauer spectra, so I got the result that okay, so what have you prepared from? Because there is a lack of specific isotope to be seen on Mossbauer. Have you faced this problem, or can comment it like that? So what I should do more properly to ensure the content of the isotope? Maybe you will be no more.
Yeah. So the main problem is that this iron Mossbauer spectroscopy is based on 57 iron, whose occurrence in nature is quite low. It's a really low abundant isotope, but and the natural abundance is basically constant, or it's constant to quite large accuracy. And in simple chemical methods, you cannot manipulate that. You cannot just prepare some isotopically enriched sample by using standard chemical methods. If you are starting with common iron source. So there is no way for chemical lab to increase the abundance of this isotope and to supply a better sample. However, if you prepare some iron oxides, if you prepare some compound containing iron, whose content is in such compound in magnetite or magnemite large enough, it will be absolutely sufficient for Mossbauer spectroscopy. And even if you coat the particles with some material, if you dilute the sample by other compounds, still the content of iron might be sufficient in terms of the total amount of this 57 iron. However, if you prepare some compound or some sample where really the final content of iron in total is very, very low, then of course also the content, the concentration of the 57 iron will be very low, and the signal measured by Mossbauer spectroscopy will be very, very low. So in such situations, there is only one possibility. You have to get the isotopically enriched iron 57, which is available on the market. It's commercially available. You can buy, for example, pure iron 57 as a metal. It's pretty expensive, but still feasible. Still feasible to if you spend some money, you can get a nice piece of such iron 57, and you can prepare a whole sample from this iron. And there will be only the isotope which is directly measured on mass power spectroscopy. So the recommendation is to prepare such isotopically enriched samples. And we considered, or we did this also in certain situations, but for compounds, for some chemical compounds whose inherent content of iron is quite low. And to measure mass power spectroscopy, we need to make all iron as iron 57. Speaking about particles, I think that all iron oxides contain enough iron, and even if you coat them with some polymers, still there will be enough iron. So maybe it's rather about quantity of the sample, or if some of your colleagues complain that the signal is poor, that there is little iron 57, you should supply maybe just the bare particles before coating them, before encapsulating them. You should supply the bare inorganic material containing the iron, where the concentration of the iron and of the isotope 57 will be high enough.
So, but the reason was that simply the source of the iron chloride was really poor in content of Fe57. So that we have checked it. So just okay. So what happened? But it was from Fluka, so there is an advertisement.
Don't buy stuff from Signal. They are repeatedly supplying chemicals, really impure chemicals. Recently we bought 2 chemicals and measured XRD, and it was a whole mess. So, but I don't know the reason for this isotope variation, but it is interesting. Like my first guess would be that the isotopic composition of stable isotopes is quite stable, is quite constant. But of course there might be some variations. It is also used, for example, in geological studies, in geological analysis. But it should not happen that it is so low, maybe, but okay, maybe that was some rare situation, maybe someone in Sigma or in Fluka confused the chemicals and they provided you some 57 iron deficient source. But just try another source, and if you have a very low amount of iron in your samples, you have to use the 57 iron. Longer time ago, I bought, like before the Russian war against Ukraine, I bought a larger amount of iron 57 from Russia. It was quite easily available there. So nowadays it will be much more expensive, but still I think affordable.
Thanks.
Yeah, very briefly. Thank you for the nice physical detailed overview. I was wondering, you talk a lot about X-ray spectroscopy to characterize the sample, but I assume this is only possible in a specific state of my sample or in a condensed state. But when I start to pack this sample in a salt or in sugar for in vivo application, does the chemical environment change these very detailed properties that we get from the X-ray spectroscopy, or can we get some discrepancies from our model we are investigating by the spectroscopy in the application?
Yeah, like the X-ray fluorescence spectroscopy was just to to analyze precisely the chemical composition of the inorganic phase. XRF was just there to analyze the chemical composition, just to be sure if you are preparing, for example, zinc-doped iron oxide, that just to be sure that the zinc is inside and what the content of zinc is. And this should not change with any subsequent modification. It should not change upon some encapsulation, upon some organic functionalization, upon dispersing the particles in any dispersion. Like if you prepare some complex magnetic phase, and if you analyze it well in the bare form, then you can be pretty sure it will remain as it is. There will be no metal leaching in the dispersion, or so it's absolutely fine to do XRF just at the beginning. And if the material is not available anymore, you could also consider measuring XRF on some modified, on some organically coated material. It does not interfere there, even if the concentration of the particles is low in the whole sample with a lot of organic stuff. It doesn't matter. You can still measure XRF and quantify the ratio of metals inside and evaluate the true chemical composition of the material.
Even in buffered solutions?
Yeah. And regarding XRD, I spent also a lot of time with XRD because I find this method really important to describe precisely the phase composition of your sample, to show the crystal structure, etc. So regarding XRD, it's better to measure XRD at the beginning when you have bare inorganic particles, when it is still not contaminated with some organic stuff, because the organic stuff it's amorphous and it will generate this background, it will generate these broad peaks, and it will distort your patterns, so it will bring a lot of complications, and you will not collect any valuable information regarding this organic stuff, regarding amorphous organic stuff from the XRD pattern. So try to measure it before functionalization. And the question, if there is any effect of the subsequent surface modifications, coating procedures, organic functionalization on the crystal structure, on these issues, this is a complex question, but typically there is no effect if no harsh chemical manipulations are involved. For example, if you use some strong acid during your surface modification, if you do some stabilization with citrate, you may disperse your particles in citric acid, in solution of citric acid. You may separate them, add some ammonia to convert the citric acid to ammonium citrate to achieve the Coulombic stabilization, and then you can run some subsequent modifications. So in that case, maybe there might be slight effect, because the citric acid may dissolve the particles partially, it may dissolve some surface layers, or it may dissolve some tiny components in the sample. Maybe it will dissolve the very, very fine fraction of particles in the sample. So afterwards, maybe your sample will be slightly changed, the size distribution will be slightly changed, or the particles will slightly decrease. They will be slightly altered. So in such a case, there might be some effect. But let's say in special cases, if you apply some stronger acid, or if you do some mass fractionation of your sample, for example, if you do some coating and then you wish to separate some particles that of smaller size that are well dispersed in the suspension, you might consider for example, centrifugation and separating the supernatant as the final product and discarding the residue. And in such procedure, you will just isolate a certain part of the sample with certain characteristic that might be different from the total. So in such scenario, I would recommend to remeasure XRD just to be sure that it is comparable.
Thank you.
Okay.
I have a question regarding Mossbauer spectra again, because you have presented quite nice Mossbauer spectra with good effect. I am really getting my nanoparticles in the solution. So I have two ways to measure them, to dose them, measure at room temperature, or to dry them and measure at room temperature, for example. Do you expect any differences between such spectra measured in the same temperature?
This is a good question. So, if the particles are, for example, coated with some material, if they are stabilized, then there should be basically no difference between the dispersed state in the suspension and the dry state without the solvent, because still the particles will be separated by the coating, by maybe some diamagnetic stuff, so they will be separated and there will be no additional effect of dipole interparticle interactions. So it will be, even magnetically, it will be very the same. So in this case, the Mossbauer spectra of the frozen sample and of the dry sample and all possible parameters and also the temperature dependence of the Mossbauer spectra would be very the same. It will be very the same for a frozen system and for the dry sample without the solvent, on condition that there is no role of interparticle interactions. And there is another assumption. During the drying, you have to protect the particles, for example, against oxidation. If your material contains also iron 2+ ions, you have to consider that the drying, for example, in air may lead to partial oxidation. You cannot dry magnetite particles in air at elevated temperature. If you have, for example, magnetite particles, you have to dry them at really lower temperatures or in vacuum. We dry them typically in a vacuum at room temperature, and in that case, there is no partial oxidation. If we had dried them at elevated temperature in air, there would have been partial oxidation to magma.
I'm sorry, I need to interrupt you. You can continue in the couloir, of course, but for
So let's discuss the synthesis of magnetic nanoparticles. Of course, this field is really huge. If you run some simple searches within Web of Science, for example, you can find for a combination of magnetic nanoparticles or magnetic particles and synthesis or preparation, you can find around 14,000 research articles. And within the search in the topics, and if you search this combination just within the title of the research articles, you will find still 1,700 articles. If you focus on review articles with the same combination, you will find around 1,600 reviews and 95 reviews with these words in the title. So the field is really huge, and also the diversity of methods that can be used for synthesis of magnetic nanoparticles is extreme. We can introduce different classifications, maybe some biologists like it, but I mean, classifications are important, but in contrast to classification of living forms, these classifications will never be natural. There is no phylogeny involved, it's just formal classification. So you can classify the synthetic methods into bottom-up or top-down approaches. You can classify them based on the main principles if they are based mostly on chemical principles or physical principles or biological principles. So you can build different artificial classifications for didactic purposes. So, but maybe more importantly, it's crucial to decide what method is suitable for your purpose, what method you should apply for your aim of the study. So there are many methods with different disadvantages, of course, but there are also some methods with some advantages. So I will try to provide some comment in this respect. The different methods provide usually different degree of control over the composition, over crystallinity, or different degree of control of, for example, oxygen stoichiometry, as we discussed, magnetite versus meghemite. Often you are also interested in the control of size and shape of particles. You may prefer some monodispersed particles. So maybe this is the most important parameters that you will evaluate if the method really provides enough control of these crucial parameters. Nevertheless, the different methods also provide the products in different forms. Maybe some experiments will lead to well-dispersed, isolated particles available in some suspension. In other methods, you will obtain just dry powder, dry or some nanocrystalline material which is interconnected by sintering bridges, or which is glued, which is somehow compact. So, and this is also crucial. If you want to prepare some particles for magnetic particle imaging, you would prefer probably dispersed particles that can be easily and individually stabilized, rather than some compact piece of nanocrystalline matter. Further, you have to consider that the different methods are also accompanied by different surface chemistry. So for aqueous, for applications in form of aqueous suspensions, you wouldn't like to prepare maybe particles stabilized with some hydrophobic surfactants that will only enable to disperse them in organic phase. And of course, the different methods provide different amounts and show different yields. There are also other issues often discussed in the literature, like energy consumption, costs of chemicals, environmental impact. But I would say that this is really not that important if we are speaking about medical applications, because these the medical applications are extremely important. They have this high gain, and for the society they are extremely important. So, like the mankind will not dispose some fascinating particles just based on somehow higher costs of the production, and it won't be about the costs of production in terms of sources, in terms of chemicals, but all the time the manpower will be the main cost. And the energy consumption, that is completely irrelevant, because also the scale of production will be probably rather low. So sometimes you can see quite strange introduction in papers on different syntheses that mention these views, but this is completely irrelevant in the medical field. So, but let us see something specific. So here is the simple classification based on the main principles involved in the production of the particles. So of course we have these physical methods, like the most simple approach is just the mechanical processing, like some milling, grinding. Many different particles can be prepared like this, that you can and sometimes you can even mix the starting elements. You can mix the constituent elements, some metals, and you can do the milling, and there will be some alloying, some alloys will be formed, or you can mix metals and, for example, sulfur, you can mill it in some high energy ball, obtaining some complex sulfide, for example, copper iron sulfur to the chalcopyrite. But there are also other physical methods, typically some lithographic methods like electron beam, colloidal lithography, and so on. These are fancy methods that will provide you with precise control over the size, over the geometry, and these methods will also enable exact positioning of particles on some substrate. These methods are connected with some substrate. But of course here the scale of production, the amount that you can prepare is extremely low. Regarding the mechanical methods, you can do this mechanical alloying by, as I mentioned, you will just mix the starting elements, you will do the milling, and at the end you will obtain some nanocrystalline material of the compound, but it will be just a whole piece, compact, maybe densified piece with nanocrystalline nature, where you can identify, for example, 10 nanometer size crystallites, but it will be a large aggregate, and then you will need to apply some special procedures to disrupt that and to stabilize individual particles. And there are also other physical methods related to application of laser, some condensation processes in the gas phase, and so on. Maybe for us, for the purpose of MPI studies and for this field, it's rather better to focus on biochemical or biological methods. And again, there is a whole plethora of procedures, starting from some historical or some old-fashioned procedures like sol gel or even coprecipitation, up to very modern procedures like maybe microwave-assisted synthesis or some specific procedures suitable just for certain groups of compounds. Biochemical methods are similar to chemical methods, but they employ typically some enzymes to, for example, to perform reduction of some metal ions and to precipitate them. Biological methods, this is also a popular direction connected to use of some magnetotactic bacteria like Magnetospirillum, Magnetococcus, Magnetovibrio, etc. You know these things very well, surely. These procedures are lovely, and they are not only limited to pure iron oxides. Sometimes you can feed your bacteria in some bioreactors also with some mixtures of different salts. You can add some cobalt 2+ salts when growing these magnetotactic bacteria, and you can produce even cobalt ferrite by biological methods, but you should not increase the concentration of cobalt too much. I think we don't have enough time to go through all the methods systematically, so I will briefly mention just something, mostly where we have some experience from our group. And I think that I will leave one method for my colleague, for Michal, who will mainly, who will probably mention something about coprecipitation. So I will skip this procedure, and I will mention that there are some related procedures that also use the same approach, but that are somehow modified. And maybe a modified version of the coprecipitation procedure can be found even in some templated synthesis, where we can, for example, do the coprecipitation in some mesoporous matrix. You can prepare, for example, mesoporous silica with certain cavities, like cavities with a diameter of 22 nanometers, using some special polymer as precursor, and then you can impregnate this mesoporous material with iron nitride, and you can do even precipitation inside the cavities and later apply some thermal treatment. And okay, there are different things you can prepare with this approach, but maybe the most known example is the synthesis of the epsilon iron oxide, which is done by such templated synthesis. Because this phase is only stable in form of nanoparticles or in form of some thin film. You cannot prepare a bulk of the epsilon iron oxide, but there is some threshold in terms of the size of particles upon which it is not stable. So if you prepare this phase within some cavities in the mesoporous matrix, you can stabilize it, and later you can dissolve the matrix. For example, here we use the silica matrix, mesoporous silica, where it was synthesized, and later we dissolved the silica with some sodium hydroxide, and we purified it and obtained single phase pure epsilon iron oxide, which is really a fascinating material because it has huge coercivity. This is the absolute opposite of superparamagnetic nanoparticles. These particles are extremely blocked. They have a coercivity of around 2 Tesla. But still, you can use them in medical applications, for example, as a contrast agent for magnetic resonance imaging, but they are not, I guess they are not very useful for magnetic particle imaging. So this is just a special example. I also mentioned this mechanochemical synthesis, for example, of the chalcopyrite, where you mix the starting elements, you do the high energy milling, and believe it or not, but you can prepare practically single phase copper iron sulfur 2. But you can see also the morphology is not very satisfying in terms of obtaining individual particles. It is just a large nanocrystalline material which contains individual nanocrystallides, but maybe some additional mechanical processing accompanied with application of some surfactants would be necessary. Maybe more useful for your purpose are the hydrothermal and servothermal procedures that can be done also with supercritical solvent. If you go above the critical points for water, it's around 334 centigrades and 218 atmospheres. So you can enter the supercritical fluid, which has some really superior properties in terms of solubility of some hardly soluble materials. But even the hydrothermal or solvothermal synthesis at lower temperatures and lower pressures is very useful. generally these higher temperatures and pressures facilitate the dissolution. And it's quite simple. You need just to have some autoclave or sealed reactor. It's often quite fast and really facile for the guys in the laboratory. And these procedures can be run without surfactants as well as with surfactants that will limit the growth of particles somehow. So to illustrate this procedure, I will show you some typical products of ferrite nanoparticles, specifically manganese zinc ferrite particles prepared by hydrothermal procedure at temperature of only 180 degrees. So in water it was hydrothermal procedure, and the overall process was very simple. We just took some metal nitrates, we dissolved them in acidic solution, somehow we set the stoichiometric ratio, and then we adjusted pH. In this case, it was necessary to apply inert atmosphere to prevent oxidation of manganese 2+ to manganese 3+. So yeah, maybe this step was a bit tricky, but you can. This system is not extremely sensitive. You don't need even a Schlenk line. If you are very skillful, you can use, for example, a glove bag and work carefully within a glove bag. And so during this adjustment of pH, adding sodium hydroxide or adding ammonia, you will precipitate some complex hydroxides or some complex mixtures containing hydroxides and oxides of manganese, zinc, and iron. And then you will transfer this precipitate, this precursor, into your autoclave, and you will do the hydrothermal treatment. As I said, just at 180 degrees for 12 hours. And you can see the resulting particles here. So these are the bare particles. No surfactants were involved. There is quite broad size distribution, but still reasonable compared to other methods, as we will see later. And these particles typically form, such particles prepared by hydrothermal method typically form clusters. They even, if you apply some stabilization, like with with ammonium citrate still, they will form some clusters. So upon coating with silica or upon coating with some polymer, you will typically observe such small clusters of individual crystallites coated as a whole with your material, either with silica or polymer. And this figure shows the typical size distributions of the crystallites involved, the size distribution of the clusters, and there is also the size distribution of the coated particles. So these are typical products that are easily obtained by hydrothermal or very similarly by solvothermal procedures in organic solvents. I would say that the main advantage is the ease of preparation, that even anyone without proper chemical training can do this very easily. There is no special manipulation. Also, the amount produced in a single batch can be quite good. Yeah, in a 50 milliliter autoclave, we usually prepare around half gram of material in a single batch. These particles are typically very well crystallized. There are no issues with some amorphous components, and the crystallinity is high compared to other methods. In this case, no surfactants were involved, so you will isolate at the end just some inorganic material, not burdened with some organic components. another method, sol gel methods. It's it's an extensive group of procedures. I think you know this very well from the textbooks, but just shortly at the beginning you have a solution, a homogeneous solution, and then you will somehow prepare a gel through evaporation of the solvent and through some polymerizations, and the gel will stabilize very homogeneous distribution of the metal cations. And later you will dry the gel. You will basically burn the gel into some fine ash, into some fine powder, which will be formed by very fine grains that will be reactive. And at the end, you will be able to heat these grains to do some chemical reaction by heating the grains, but the temperature needed for that will be significantly lower compared to the classical ceramic procedure. If you prepare some complex oxide from commercially available chemicals by the ceramic procedure, you need to mix the components thoroughly, and you need to apply high temperatures. But in this case, because of this process, because of going through the gel and through the incineration of the gel, you will get such fine precursor that can be reacted at much lower temperatures. So, for example, one procedure that belongs to this group is the citrate procedure, where you use citric acid that forms some complexes with metal cations. There can be different coordination modes of these citrate anions, but you can imagine some complexation of the metals in solution. But you will add also ethylene glycol. You will add some glycol inside, which will, during heating, react with the citric acid, with some free carboxylic acids of the citric acids, and there will be esterification. So it will polymerize through forming esters, and also there might be even formation of ether bonds during the reaction of the hydroxylic group of the citric acid and hydroxylic groups of the ethylene glycol. So this is the way how chemically the gel is formed. Then later you will dry it, you will burn it, obtaining some poorly crystalline mixture containing these fine particles, and at the end you have to heat it. You have to heat it, and depending on the target phase, depending on the system under preparation, you may need to go even to elevated temperatures, to quite elevated temperatures. In the first part of the presentation, I mentioned specifically this lanthanum strontium manganite, which can be easily prepared by this sol gel procedure, but you need to apply at the end temperatures of around 600-700 degrees, maybe for several hours, and at such low temperatures, comparatively low to the ceramic route, but at such temperatures and for the treatment of several hours, there will be no really huge grains, only smaller grains will arise. So at the end you will obtain such nanocrystalline material formed by 20 to 70 nanometer sized grains, but the grains will be interconnected through sintering bridges. They will be connate. It won't be formed by individual particles, and you need to apply some mechanical treatment to separate the individual particles, maybe by rolling and milling. So, and by the way, this is practically the only reasonable way how to prepare nanoparticles of such complex perovskites. So the product is not very fancy in terms of the size distribution, in terms of the shape control. The distribution of particle sizes is really broad, and it is further it is further increased by applying this mechanical processing. But this is the only reasonable way how to prepare such special particles, and they are really special in certain terms. Actually, we were interested very much in particles of this phase, and we were trying to find some other procedure, some alternative procedure, something more sophisticated that would enable us to achieve better control over the shape of particles and the shape and over the distribution of sizes. So we tried to prepare these particles in flux. It means in some molten salt or in molten hydroxide, and at the end we were somehow successful while preparing these particles in molten sodium nitride. Maybe the size distribution of these particles is also large, but we achieved like well dispersed or partially dispersed particles of predominantly cubic shape. We were very happy. It was a new synthesis, quite tricky in terms of manipulation, because we were using a large volume of molten sodium nitride, or at certain experiments also of sodium nitrate, which is, you know, not very compatible, for example, with organic stuff. If you mix this a strong oxidizing reagent with some in molten form with some organic stuff, it may cause big troubles. But it was something new. We were happy, and we studied these particles, and we revealed some interesting features there. Actually, these particles were extremely different to the salt gel particles, to the particles prepared by the first method I mentioned. And maybe from the practical point of view, the major issue was that the magnetization of these particles was strongly reduced. The magnetization was reduced not only compared to bulk samples, but also compared to the salt gel particles. We really spent a lot of time, and we spent maybe a lot of funding while analyzing these particles and doing some fancy studies. It brought many papers, and maybe the material was not worth of that from the application point of view, but it was really fun. And we found out that these particles from the flux, from the synthesized in the molten salt, are more complex than the particles from the salt gel procedure, because the flux was strongly oxidizing, and actually the flux was oxidizing manganese at the surface of these particles to higher oxidation state. You know, in this perovskite phase, where lanthanum as trivalent cation is combined with strontium as divalent cation, you have manganese in the oxidation state 3+, and in the oxidation state of 4+, whose ratio should be given by the ratio of the lanthanum and strontium. But in the case of this synthesis, due to the strongly oxidizing environment, some manganese at the surface layers was oxidized to manganese 4. Some manganese 3+ was oxidized to manganese 4, and there was some effective oxygen excess, because the surface of the particles were saturated with oxygen. And this somehow altered the magnetic properties and the fundamental properties of these particles, because this perovskite phase has a very, very complicated magnetic phase diagram depending on the ratio of lanthanum and strontium. Depending on the ratio of manganese 3+ and manganese 4+. It's fascinating. It's very, very, very rich and complex. And by this synthesis, we shifted the particles from the nominal composition with certain ratio of manganese 3 plus and manganese 4 plus to a higher region of region of higher oxidation, and these particles behaved like containing more strontium 2 plus than they actually contain. And for example, at the end we found that they have complex structure with ferromagnetic core, antiferromagnetic shell, and above that there is another magnetically disordered shell. And we even evidenced certain gradient of strontium within the particles, that the concentration of strontium was increasing towards the surface layers because of some kinetics of the growth of particles in the flux. So maybe I'm going too much into details, but I'm just showing that you cannot disregard the synthesis. You cannot disregard the procedure. It is not only about the nominal composition, about the size of particles, but the different synthesis can really affect the material extremely, and the different synthesis can shape the final properties and can completely alter the properties. A very popular method is the thermal decomposition, and I guess that we don't have much time for that, but no time. Okay, just this is the concluding remark, that ferrite particles are easily prepared by thermal decomposition, which provides nice monodispersed particles, but coated with hydrophobic surfactants, and you have to deal with some special chemistry to get them into aqueous suspensions.
Okay, so are there any questions regarding this presentation? If not, in